Question 4. Shot put is an Olympic event. Imagine that. And apparently the shot is a heavy ball. You probably knew that already. We've got to work out the amount of time taken for the person to throw. The amount of time during the throw when the shot is in the athlete's hand. So we know that each picture is taken every 0.1 second. So this from here to here is 0.1 second, 0.2 seconds, 0.3 seconds, 0.4 seconds, and whoop, it's gone at the 0.5 second mark. We don't know quite at which point between this picture and this picture it's been released. So we know it's taken as long as 0.1, 2, 3, 4 seconds, and we know it's done by 0.1, 2, 3, 4, 5 seconds. We know it's between 0.4 and 0.5. So if you put any answer from 0.4 to 0.5, including 0.4 and 0.5, then they would have given you the mark. Explain how the scientists could improve this method of analysing the throw. This method. Some people got into all kinds of weird and wonderful ideas of analysing the throw, which was lovely. It wasn't answering the question. We needed to improve this particular method. So the idea is, at the moment, we're not really sure when it leaves the hand. So we would really like to know more exactly when it is. Is it at 0.4? Is it 0.5? Is it somewhere between the two? Your best bet is to take more photos more frequently. So instead of taking it every 0.1 second, maybe take it every 0.01 second, maybe, or every 0.05 seconds, or something like that. That will help us to see, and then that way you'll be able to know when, more exactly when that shot put is released. So 1 mark for saying take pictures more frequently, 1 mark for saying in order to determine the exact time of the release. It says other responses may be acceptable as well. Okay. But it had to be for that particular method. You couldn't come up with an entirely different method. Right, the average acceleration is 20.6 meters per second squared. The mass of the shot is 7.26 kilograms. Calculate the average force. Right, so again, let's have a think about how we're going to solve this. We're given two numbers. We're asked to calculate a third. So let's write down what we have. We know the acceleration A is 20.6. We know the mass M is 7.26. We've got to find F. Not sure what that is. We need an equation with F, M and A. F equals MA seems like a good fit. F equals MA. We write the equation, then we put the numbers in. Remember, you can get more marks that way, or at least, you know, if you get the final answer wrong, you've got the chance of getting working marks. F is M times A, so it's going to be 20.6 times 7.26. Which, if you whack in your calculator, you will end up with 150. Of course, technically, you won't quite end up with 150. Let's prove that. So if we do 20, let's get it in the screen there, 20.6, going to multiply it by 7.26. There you go, 149.556. That seems like too many decimal places, doesn't it really? We should be rounding. So that's why they're going with 150. 150, three significant figures, seems to be a sensible way of doing it, particularly seeing as there's three significant figures for these two numbers there. So there you are, 150, and of course, newtons. Of course, that was given in the question, so you didn't have to worry about that particular one. Okay, in another throw, we've got a second calculation question here. So let's get our numbers down. We know the shot is in the hand for 0.48 seconds. It's another throw, so we've got to be a little bit careful here. We're not going to use data from the old throw. 0.48 seconds. The average acceleration during this time is 23 meters per second squared. So A is 23. S to the minus 2. You don't have to put the units in when you're putting these things in. I've dropped the mark scheme. Let's pick it up. There we go. Okay. So we're going to figure out how this works. We've got to work out the velocity. So we need to know what v is. We do not know what it is. Now looking at this equation, we're probably going to want to use v equals u plus at. Now thinking about it, I've got a feeling that this is often given in GCSE as the acceleration is the change in speed divided by the time taken. You can rearrange that by multiplying both sides by t, you'll end up with AT is equal to V minus U. And then if you add both sides, add U to both sides, you'll end up with U plus AT is equal to V. We often use this equation just on its own in A level, V equals U plus AT. It's just rearranged from the equation that you're familiar with. So you get a mark for rearranging that properly. The nice thing is that U, the initial speed, is 0, because remember he's holding it in the first place, and then, you know, during the throw he pushes it forwards. That incidentally is exactly how you want to throw a shot put if you want to get a world record. So V equals U plus AT. We can ignore this U because U is 0, so V is AT, so we're just going to take A and times it by T. 0.48 times 23 is going to give you 11.04 meters per second, or, you know, to round it up, 11 meters per second would be absolutely perfect. So it's going at 11 meters per second as it leaves the athlete's hand, and again they've given the unit, so you don't have to worry about that. In another throw, oh guys, guess what? It's another calculation. This one was a nice one, but we missed. A lot of us missed the mark on it because we forgot one crucial detail. So, calculate the amount of gravitational potential energy gained by the shot. Right, so we're wanting an equation of gravitational potential energy. You've got one, GPE equals mgh, often remembered as PE equals must go home. And we are going to put those three numbers in, and it will just tell us what gravitational potential energy is. So what's M? M is 7.26. Let's go off the screen. Okay. We need to know G, we need to know H. G is the thing that a lot of people forgot. It's 10 on the surface of the Earth. I think we can safely assume that this Olympics is on Earth. And then finally the height, it goes up 1.3 meters. So whack that in. MGH, MGH, put the numbers in. That will give you overall, I could stick on the calculator, but I've got the mark scheme right in front of me, so let's cheat. 94.4. And that, of course, is joules. Again, they've given you the unit, so you didn't have to worry about that. But yeah, MGH. Don't forget the G. The G is 10. Sometimes you might have heard it being described, by the way, as 9.8. That is slightly more accurate, but it's not the accuracy that we need at GCSE. We're just going to stick with 10. So we have 94.4 joules. The final question, again, a little bit of a mean one. Let's see if we can unpack this. Let's see first of all if we can turn a page, like an adult or child might be able to do. Right, okay, the scientist examines the images to find ways of increasing the momentum of the shot without the athlete using any extra force. This was a key thing. If I'm honest, I've only just spotted this. The amount of times that students were talking about how to increase the force. I didn't even bother reading the question, I was just marking it. But lots of people said, oh well, you can increase the force by... Don't do that, we're not supposed to. So the scientist has advised him to lean further down at the start and make his arms straight before he releases the shot. Let's see if we can work out why that would be the case. We're looking for 3 marks, so a bit of detail on those 2 points and you should be fine. Why lean further down at the start? Well, if you lean further down at the start, you know what? Starting to get that feeling that I'm going to need to draw a stick person doing something unusual. This isn't going to go over well. There he is. Let's stick a little face on him so we know where he is. He's going to fire this. He's leaned all the way down there, and he's going to go shoo, all the way there to launch the shot. If he leans further down, he's going to be travelling a further distance before he lets go of it. So yes, he's still applying the same force the whole time, but he's applying it across a longer distance. You remember from the energy equation, the work done, W equals FD, work done is force times distance. So if we have a larger distance, even with the same force, we're going to be transferring more energy. It's going to be moving faster by the time it gets to the end. Make his arms straight before he releases the shot. Again, that's going to increase the time and the distance. You know what, guys? We may have muddled that slightly. Pretend that didn't happen. What we're looking at, let's take this from a slightly different perspective because it's written in a particular way in the mark scheme. What we're looking at is ways of increasing the time and the distance that we're travelling. We've already seen that increasing the distance will mean that we end up sort of giving it more energy and increasing the momentum that way. You can also do it by increasing the time. So the way that you can figure this one out, and in the mark scheme, as you'll see later, they like it if you use an equation to kind of prove this. If you look at the equation for force is mass times acceleration, and we know that acceleration is just the change in speed divided by the time taken. So what we can actually do is we can just multiply that bit at the top. It's just going to be basically, and I'm just going to stick an extra step in here just to be absolutely sure what's going on here. This equation is m brackets v minus u over t. So that's basically mv minus mu, isn't it? All over t. So the force is basically the change in momentum divided by the time taken. And finally, what you can do, if you multiply both sides by t, and I know we're going sort of a little bit beyond where we'd usually expect a GCSE class to be getting, but this shows it quite nicely. The change in momentum, this is the final momentum minus the initial momentum, the change in momentum is going to be really big if we have a big force or a big time. Okay? Now we've already said we can't increase the force, so we can increase the time. Let's increase the time that the shot put is in our hand. If you straighten your arm, you're going to be doing it for a longer distance and therefore a longer time. If you lean further back, you're going to be putting in again a longer distance and a longer time. So if you bring those ideas all together, you can get where they're looking at the mark scheme. So the distance is greater, there's 1 mark. The time when we're applying the force is longer, 1 mark. Use the equation, F is the change in momentum over the time taken, we just talked about that, for 1 mark. They would also give you a mark if you mentioned that the momentum could be increased if you increase the final velocity. That's your equation, momentum is mass times velocity. So that was perhaps an easier way of getting one of those marks. If it's going faster, it'll have more momentum. They would have given you a mark for that. You've got these extra bits as well, so you can just check here that was a more complicated way of doing it. These x's, by the way, are times is v squared minus u squared equals 2 times a times d. D meaning distance. I don't know why they've done it because in the real equation, of course, it's 2ax. But let's worry about that another day.